Earth is an ancient planet that has existed for over 4.5 billion years, similar to other planets in the solar system. All of them formed simultaneously with the Sun. But 4.5 billion years is just a very short span compared to the lifespan of the universe, and it is almost certain that many other planets formed long before that. However, in the early stages of the universe, planets did not yet exist. At that time, only hydrogen and helium combined to form stars, not the worlds as we know them today. Much later, when the cosmic gas had evolved, the first planetary systems gradually took shape. Determining the formation time and initial shape of the first planets is a complex issue, requiring careful consideration of many factors. However, by studying exoplanets in the Milky Way, we have come to realize that primordial planets may be far older and stranger than initially imagined. How are planets formed? To determine when the first planets were born, we must first understand the process of planet formation. Scientists have gained a fairly clear understanding of this issue thanks to a series of successful research missions into the formation of new star systems. We all know that stars and the planets orbiting them form from isolated cold gas clouds drifting in the universe, containing many diverse elements and compounds, but the main components are still hydrogen and helium. These clouds have an asymmetrical structure, which causes them to continuously break apart and interact with each other inside. Perhaps it will eventually collapse under the force of gravity. This process compresses matter from the gas cloud into a compact, dense, and scorching hot core. Finally, this seed will grow into a new star, with the surrounding gas layer compacted within an enclosed chamber like an oven, continuously replenishing gas for the inner particles. When the protostar reaches a certain mass, approximately 80 times that of Jupiter, it erupted like a nuclear reactor, blazing brightly and unleashing violent surges of energy, tearing apart the shroud of mist that enveloped it. After that, the expelled gas gradually accumulates into a blazing hot accretion disk, swirling around the star and lasting for about 10 million years. At this stage in the young star's life cycle, the process of planet formation officially begins. All planets in a star system form from the material in the accretion disk surrounding that star, and this process occurs within 10 million years. When the accretion disk is depleted, no new planets can form around that star. When this process begins, the accretion disk will be so dense and hot that no matter can form within it. But when the young star emits streams of light from its corona, some of the material is pushed outward, causing the temperature inside the gas disk to drop to a threshold that allows all formation processes to begin. Initially, the condensed particles form tiny, fine crystals, which then combine with other particles to form larger masses of matter. In the next few 100,000 years, dust particles several centimeters in size will gradually form. At this point, they had grown large enough to begin generating significant gravitational force. This helps them attract and accumulate dust from the surrounding disk, increasing their mass and bringing them into the range of other clumps. For about 1 million years or more, this process formed massive rock formations over 1 kilometer long, known as plain testaments. Then, these rock fragments orbited within their gas and dust disk, accumulating more dust and colliding with other rocks, gradually forming the planet's core from the bottom up. The heavier an object is, the stronger its gravitational force, thereby dominating the surrounding space. Facilitate favorable conditions for larger objects to rapidly accumulate on the expanding surfaces of smaller ones. And so, in just 100,000 years since the planets were born, the majority of the planetary mass in the system will concentrate into a few dozen spherical rocky cores smaller than Earth, known as planetary embryos. If these planetary embryos are quite close to their parent star, then the collisions themselves will determine their ultimate fate. After the planet formation stage ended, dozens of planetary embryos collided and merged, forming several rocky planets like Earth, Venus, Mars, and Mercury. Additionally, if a new planetary embryo forms at a location much farther from its parent star, it may lie in a region cold enough to develop into a different type of planet. The passage consists of volatile substances that have solidified, such as methane, ammonia, and ice, rather than rocks. When cooled to a sufficiently low temperature to exist in solid form, these substances become an abundant supplementary material source for planet formation. This phenomenon can cause giant planets, with masses more than 10 times that of Earth, to form rapidly. If this happens early enough in the planet's formation stage, the icy layer will capture the floating hydrogen and helium atoms in the protoplanetary disk before they are swept away by the strong stellar winds emitted from the central star. These light elements accumulated in the planet's atmosphere, gradually forming a dense, suffocating layer. The gas at this critical point liquefied and continuously expanded, giving rise to a gas giant like Saturn or Jupiter. These worlds may have diameters dozens of times that of Earth and masses hundreds of times greater. However, not every icy planet that reaches 10 times Earth's mass manages to capture hydrogen and helium, as most of these elements had already dispersed beforehand. However, these planets could still retain a dense atmosphere, containing volatile ices, although the amount of such material is not as abundant as in gas giants. Therefore, these planets are called ice giants, such as Uranus and Neptune. No matter what form it takes during the planet-forming stage, by the end of the process, the accretion disk will completely vanish, either absorbed by planets or scattered by radiation, and no new worlds can emerge afterward. Therefore, this is a fairly convenient method for astronomers to determine the age of a planet, as all natural satellites within the same star system form simultaneously and have ages comparable to their host star, differing by only a few million years. To determine the age of a planet, we only need to know the age of the star it orbits. Methods for determining the age of a star. To determine a star's age, we need to know its metallicity. The metallicity of a star is the proportion of elements heavier than hydrogen and helium in its composition. Although this ratio typically makes up only a few percent, it is still significant enough to noticeably influence the star's physical properties and evolutionary process. Metal. In this case, elements such as oxygen, carbon, nitrogen, and magnesium are all considered metals. The planet formation process we just mentioned requires these metals. Without them, dust particles and matter on the planet would not be able to coalesce, and self-attracting objects could not form. And there's only one place we know where metals like these are forged: deep in the cores of stars. Stars shine due to the process of nuclear fusion. In this process, light atomic nuclei combine to form heavier and more complex nuclei, including metallic elements. When the universe was just about 200 million years old and the first generation of stars began to shine, metals did not yet exist. Only hydrogen and helium remained after the Big Bang. Therefore, these stars are almost entirely composed of primordial light elements. They live brief and turbulent lives, ending in a supernova explosion. But in their brief shining moment, these stars are believed to have forged the universe's first metallic elements. They transform the fuel in their core into elements such as lithium, nitrogen, argon, and ultimately iron. When these stars end their life cycle and explode, the metal elements are ejected into the surrounding gas clouds. Between the stars lies a hydrogen environment containing heavy elements. Each stellar explosion contributes to the ongoing chemical evolution of the universe. In the following times, the gas clouds continued to contract and form new stars. During this process, metals were also mixed in. Ultimately, this facilitates the formation of more stable stars with longer lifespans and higher metal content. From this, we can determine the linear relationship between a star's metal content and its age. A star with higher metallicity formed later, as it required more gas from previous supernova explosions. This indicates it is a young star. Additionally, metal-poor stars clearly show a deficiency of heavy elements. Therefore, they must have appeared when the universe was not as dense as it is today. Thus, these stars are likely among the most ancient. As mentioned earlier, metallicity would be nearly zero in the oldest stellar generations, meaning planetary systems could not have formed that early. But at some point, it seems the universe crossed a threshold where stars contained enough metal to begin forming planets through accretion. Therefore, the key to determining when the first planets were born lies in understanding when the universe contained enough of the necessary materials. To accurately determine when this event could have occurred, scientists spent decades exploring the Milky Way, searching for its oldest stars and planets. Exploring planets beyond the solar system. Initially, there were two main methods for detecting planets outside the solar system. First and foremost, this method relies on detecting when planets pass in front of their host star, blocking the light source as observed from Earth. The second is detecting fluctuations in a star's spectrum caused by the influence of companion objects. However, both of these methods have certain margins of error, making our initial understanding of the number of planets in the Milky Way inaccurate. Both methods make it easy to detect giant planets, comparable in size to Jupiter, orbiting their host stars. This type of planet is called a hot Jupiter. They are giant gas planets that formed at a great distance. Then, they moved inward and accumulated material at the current distance we observe, where they produce the most noticeable fluctuations and move most frequently. Enhances our ability to observe. Since the mid-1990s, hot Jupiters have become the most frequently detected type of exoplanet in the initial surveys. This led scientists to conclude that they are a common type of planet outside the solar system, while also serving as a reliable indicator that stars could potentially harbor life on their planets. But the issue here is that hot Jupiters are commonly found in metal-rich star systems with more dust. To reach such enormous sizes, a gas planet must absorb vast amounts of rocky material and volatile compounds, resources that are extremely scarce in metal-poor primordial star systems. Later, scientists only detected Jupiter-like gas giants in metal-rich star systems. And since they made up the majority of exoplanets discovered at that time, this led to the mistaken conclusion that a planetary system needed to have a metal content similar to the Sun in order to form. And that region of space would not become dense enough until 6 or 7 billion years after the Big Bang, only about half the current age of the universe. This is a long period without the appearance of any planets, which will severely impact the possibility of extraterrestrial life existing elsewhere in the universe. However, as we entered the 21st century, the scientific community gradually realized that this was not entirely true. Thanks to modern observatories like Hubble, Spitzer, and Kepler, the tracking of motion and detection of oscillations are now entirely computer-operated. Today, with the ability to observe thousands of stars simultaneously and detect even the most isolated satellites, scientists have identified over 5,000 exoplanets of diverse sizes and types, some of which have existed for up to 10 billion years. Among them, the oldest and most magnificent world is the hellish planet BSRB-12620-26b. This planet is also known by its unofficial nickname, Genesis, the oldest planet in the universe. To date, it is the most ancient planet ever discovered, located approximately 7,200 light-years from Earth in the orbit of the star Scorpios, near the center of the ancient globular cluster Messier IV. For a long time, scientists believed that stars in globular clusters could not host planetary systems. The scarcity of metal, combined with the effects of opposing tidal forces and the intense stellar winds emitted by these closely orbiting stars, is predicted to disperse the protoplanetary disks before they can condense. This renders the process of planet formation impossible. Therefore, scientists never thought they could find a planet existing within such ancient and harsh star clusters. The initial observations by scientists of globular clusters seemed to confirm this, as they found no signs of any hot Jupiters existing within them. However, the situation at Messier 4 is entirely different. In 2003, astronomers used the Hubble telescope to discover a group of helium and metal-rich white dwarfs, estimated to be up to 13 billion years old. This makes them among the most ancient stars ever discovered, while also linking the existence of life to one of them, despite the harsh environment surrounding neighboring stars, where the planet Genesis formed. This discovery shattered multiple records in the field of planetary science. Not only was it the oldest planet ever discovered, but it was also the most distant planet recorded at that time. Genesis is not only the first planet in the globular cluster, but also the first exoplanet discovered to have a binary orbit, simultaneously revolving around two stars. One of the binary star systems in Genesis is PSRB 1262026. This is a pulsar. Essentially, pulsars are rapidly spinning neutron stars, so fast that S wavelength to distort into a double cone shape, with the apex pointing toward the star. This allowed scientists to identify the system in 1988. In the following years, they continued searching for other companions by observing the disturbances they caused in the host star's spectrum. Almost immediately, astronomers detected the existence of a second object in the system, the white dwarf WDB 162026, an ancient star. This is the exposed core of a dead star, with a mass too small to have exploded as a supernova. Even as late as the 1990s, scientists still hotly debated the possibility of a third object orbiting outside this binary system's center of mass. This object was hypothesized to be either a small, low-mass star or perhaps an unusually large planet. In 2003, scientists finally confirmed the existence of a planet using the Hubble Space Telescope. Named PSRB 12622026b, this planet was described as a type of hot Jupiter but with a mass roughly 2.5 times that of Jupiter. Scientists suspect whether Genesis is a true natural satellite of this system, as it orbits the chaotic region at a distance of 23 astronomical units with a wide trajectory and a hostile surrounding area. Instead, researchers suggest that this planet initially formed in a more distant region within Messier IV, orbiting an isolated star surrounded by a dust disk. Later, gravitational disturbances ejected it from the local neighborhood and directed it toward the center of the vegetable cluster. Then, it was swept into the whirlwind of a fierce tug-of-war between ghost stars, where it continues to orbit to this day, completing one orbital cycle around the system every 100 years. However, if this planet formed somewhere within Messier IV, it would likely share the same age as the rest of the Rao cluster, where hundreds of thousands of stars were born rapidly in the early universe. This suggests that Genesis is estimated to be up to 12.7 billion years old, an astonishing figure that completely overturns the previous belief that planets could only form around metal-rich stars. Existence is that it. The KEPLER 444 planetary system is the oldest known rocky planet system ever discovered. In 2015, astronomers using data from NASA's Kepler Space Telescope announced the discovery of a new planetary system, named KEPLER 444 after its central star. This is an ancient triple star system, located 119 light-years from Earth. At its center is a small orange dwarf star, which hosts 5 rocky exoplanets. These planets vary in size, ranging from Mercury-sized to Venus-sized, and all have stable orbits. Unfortunately, none of these rocky planets are considered capable of supporting life. All of them orbit their parent star at a distance closer than Mercury is to the Sun. This makes their surfaces extremely hot and incapable of sustaining life. However, with an estimated age of over 11.2 billion years, these planets show that rocky worlds have existed as long as the gas giants. Both types of planets can form in most parts of the universe where life exists. Their emergence depends far less on the type of host star than we once thought. After thorough analysis, we can confirm that the planet formation process, regardless of how it occurs, is both robust and adaptable, capable of functioning under various conditions, even in the absence of heavy metal elements. There could be countless planets in the universe, with each galaxy containing hundreds of billions of planets diverse in type and age. The first habitable planet. The next question we need to answer is, if rocky planets have existed for most of the universe's history, how long after their formation does it take for them to become capable of sustaining life? If rocky planets in the universe have had over 10 billion years to reach equilibrium, this would essentially increase the likelihood of extraterrestrial life existing elsewhere in space. However, for life to exist, a planet must meet far more precise and intricate conditions compared to other worlds. To transform a rocky planet into a habitable one, we need a full range of complex factors, such as a temperate atmosphere, suitable chemical compounds, and balanced energy distribution. And most importantly, a liquid environment to mix molecules, facilitating the chemical reactions that give rise to life. On Earth, fresh water exists in liquid form and has flowed across the planet's surface for billions of years. However, other liquids such as ammonia also possess hydrogen bonding properties, a key factor in biochemical processes. From there, we can imagine countless chemical formulas that led to the formation of life. However, the essential element that every recipe for life requires is time. The conditions of balance and stability must be maintained continuously over long periods, uninterrupted for hundreds of millions of years or even longer. To ensure sufficient time for the complex and unpredictable chain of reactions involved in the formation of life's first generation of stars from debates about the possibility of life. Besides lacking the necessary chemical compounds, these primordial stars also did not exist long enough in any one place to sustain the process of planetary system formation. The rivers of Zen will also overflow with starlit winds, the shockwaves from supernovas and dark cosmic energy powerful enough to annihilate all nascent life. But as the rate of star formation in the early universe slowed, galaxies would almost certainly begin to produce rocky planets capable of supporting life after a few billion years. However, whether these worlds can ultimately become habitable depends on how many times the conditions for life to arise have occurred. Galactic habitable belt. Galaxies like the Milky Way typically undergo chemical evolution from the inside out, with most metal-enriching supernova explosions occurring in the densely populated galactic core. The closer to the galactic core, the higher the metal density. Conversely, in regions farther from the center, stars are more sparsely distributed and less influenced by supernovae, limiting their ability to accumulate metals. Therefore, it was once believed that the outer regions of the Milky Way and spiral galaxies were barren wastelands, with almost no planets existing there. Estimates of the likelihood of life. But recently, we've observed that planets can still form in metal-poor environments, even just a few billion years after the Big Bang. The question arises: how can such vast regions of space in the galaxy contain enough necessary matter to form planetary systems from such an early stage? Scientists have probed the depths of the cosmos to determine the metal content of the most ancient galaxies, using the background light from quasars as an illuminating source to conduct spectroscopic analyses. They discovered that metal levels similar to the Sun could exist in galaxies with redshifts up to Z=10, meaning approximately 13 billion years ago. Ultimately, the detection of metals in these ancient galaxies is no surprise, as the star formation rate during that period reached its peak, leading to a significant increase in the number of metal-producing supernovae. But in the early stages of cosmic evolution, about 1 billion years after the universe formed, scientists predict that the amount of newly synthesized metals was still very small and concentrated only in a relatively small region near the core of the bustling Dongduck galaxy, where most star formation occurred. But instead, scientists were utterly astonished to discover traces of metal in primitive galaxies located 50,000 light-years away from their corresponding cores. From the very beginning of the universe's formation, a small number of metals were created and are still spreading throughout their host galaxy. The rapid spread may have been caused by the radiation emitted from the stellar explosion. Newly formed metallic elements at the galaxy's center are pushed outward toward the outer ring. During that era, the dynamic star-forming regions emitted stellar winds so intense that they could sweep away all metals released by supernovae. These elements will be expelled outward by radiation pressure, carrying them farther to seed metal-poor star systems, beyond even the newly formed heavy elements. During that period, the extremely intense stellar radiation made these young galaxies uninhabitable. But after the stars explode and end their life cycle, they leave behind vast clouds of gas spread across their host galaxy. This significantly increases the number of potential planetary systems, thereby expanding the corresponding habitable regions in the galaxy, nearly encompassing the entire expanse of space. This could lead to countless habitable worlds forming across galaxies and the universe. Once all the necessary conditions were met, life could have emerged very early, across vast regions of space where habitable planets formed. The likelihood that one of those worlds independently awakens life apart from us is growing ever higher. Unfortunately, we had to wait until scientists discovered undeniable evidence of that in another region of the universe. We can never be certain about the number of worlds where life could exist. Even if the galaxy is filled with temperate ocean planets and Earth-like worlds. Here are two natural English translations of your Vietnamese text, with slight variations in phrasing while preserving the original meaning.